and then we need a catalytic strong acid, which is usually 12 molar HCl. So the acid source is actually going to be protonated ethylene glycol. This is what's going to protonate that carbonyl group, thus generating the actual ethylene glycol. So your first step is proton transfer, but the source of that proton is different. After that, ethylene glycol can then attack and push the pair of electrons back onto oxygen. Giving you that intermediate. And then another molecule of ethylene glycol is going to act as your proton shuttle to take this proton off here and put it on there. And you'll recognize that intermediate there as the hemiacetal. Water can then leave, and you can either just have it leave, or you can push it out with a lone pair from the other oxygen. I showed it being pushed out last time, so I'll show it just leaving today. And then because this is an intramolecular reaction, the likelihood of this lone pair on this other oxygen colliding with that through a 5-member ring is quite high. So this step is enhanced by the fact that it's intramolecular. Generating that intermediate, and then we will get the final product by simply taking that proton off. And that regenerates our original protonated ethylene glycol that we used in this first step. So step 1, right, is proton transfer. Step 2 is nucleophilic attack. Step 3 is proton transfer, as is step 4. Step 5 now is the loss of the leaving group. In this case, the leaving group is water. Step 6 is another nucleophilic attack. And step 7 is our final deprotonation. So the mechanism is identical to the mechanism with methanol, except that the alcohol is now this glycol that has the 2 away groups within the same molecule. Right? Everything else is the same order of steps: protonation, nucleophilic attack, 2 successive proton transfers to get the proton onto the water leaving group, loss of the leaving group, second nucleophilic attack to get that second carbon-oxygen sigma bond made, and then the deprotonation at the end. So that's 7-step mechanism, both forward and backwards. Is the key also to thioacetal formation. And I'm not going to cover thioacetal formation in class, but there is a homework problem on it, where the difference is that instead of a Bronsted-Lowry acid, a proton donor, the thing that activates the carbonyl oxygen is a Lewis acid, electron pair acceptor. So you can activate a carbonyl group like this towards attack by a nucleophile by using a Lewis acid. Boron trifluoride is common, zinc chloride is common, tin, stannate chloride, SnCl4. These are all Lewis acids that are electron deficient as their central atom. you can bind to the carbonyl oxygen to generate something that has that positive charge on the oxygen, and therefore makes this very susceptible to attack by a thiol. A very common thiol that's used to solve the entropy problem and make a cyclic intermediate is this 1,3-propane dithiol. And that's the one I use in the pre-recorded videos to show you the reaction. Okay? So nothing has really changed except the nature of the acid that is activating the carbonyl group for nucleophilic attack. But I'm not going to spend time going over that because that's not significantly different from the reaction with alcohols. What I do want to spend some time on today is going over what happens when we switch from a group 6A element, oxygen or sulfur, to a group 5A element, nitrogen. So we're going to give nucleophilic conditions of nitrogen nucleophiles. And you'll recognize that nitrogen nucleophiles are amines. So we can use a variety of amines and if we use primary amines, the products are what's called imines. Imines have a carbon-nitrogen double bond in them. And if we use secondary amines, we actually get what's called an enamine, which is much like what you would think. It has an alkene in it as well as the amine function. One of the common amines that's used for that is this 5-membered ring, which is based on that cyclic amine, and that's called Protonated. And you'll notice the difference is this has 2 groups attached from the original amine, whereas this group only has 1 R group attached. And that's the difference between coming up with a carbon-nitrogen double bond and a carbon-carbon double bond in the product. Tertiary amine won't react. But ammonia will. To give you an imine, but one with a hydrogen on it. So we want to understand the difference between the addition of the nitrogen nucleophile and the addition of the oxygen nucleophile, because we're not getting the equivalent product that has the 2 carbon-nitrogen sigma bonds that you might anticipate if this mechanism went the same way for the nitrogen nucleophiles as it did for the oxygen nucleophiles. Usually these are catalyzed by acid. And just as is the case for the acetal formation, that stearochromic acid is usually 12 molar HCl in small quantities. Many times, because amines are quite soluble in water, these reactions can be done in an aqueous system, or at least in a mixed solvent of water and something else like acetone or ethanol. So let's think about what the mechanism would look like for a carbonyl compound, just a generic carbonyl compound. And just to make it quick and easy to write, let's use a really simple one. Let's use acetaldehyde or ethanal. And we're going to put into this reaction catalytic quantities of 12 molar HCl, and we're going to put in a primary amine and we'll use hydroxylamine in this case, NH2 with an OH group attached. So what would you expect would happen? Obviously 12 molar HCl is really hydronium ion and chloride ion, right, with a little water present. Because as soon as we dissolve the hydrochloric gas in that water to make the hydrochloric acid, it dissociates. So this is what's in solution, right? We've got hydroxylamine, we've got our aldehyde, and we've got the hydronium ion. And chloride, but chloride's a spectator ion, so we don't really care. So what would you expect would happen if we mix those three things in solution? What would be the first thing that would come to mind?
Protonating the carbonyl oxygen.
That would be directly analogous to what we did for the acetal formation, right? But is that carbonyl oxygen the strongest base in the system?
Attack the.
Because this acid is going to be looking for the strongest base it can find. So what are your bases? What are your choices?
The hydroxyamine will be attached by the acid.
So this is a better base. That nitrogen lone pair is a better base than the carbonyl oxygen. So the first thing that's always going to happen when you put a strong acid in the presence of an amine is the nitrogen of the amine is going to get protonated. So we don't really actually have hydronium ion anymore. What we really have is the protonated version of hydroxylamine. Just as in the reaction I just showed, where we have ethylene glycol and catalytic strong acid, the first thing that happens is the catalytic strong acid protonates the ethylene glycol. So we have this. And we have that. The pKa of this guy is significantly less than the pKa of hydronium ion. pKa of hydronium ion is about -2, -1.75. The pKa of protonated amines is more on the order of 9. And the pKa of protonated carbonyl compound is actually on the order of -6 for most of the protonated carbonyl compound. So this is a pretty strong acid. In the presence of hydronium ion, it'll get protonated to form this, but this isn't really a good enough acid to protonate. The carbonyl group. Not to any meaningful extent, anyway. So there's going to be a difference in the order of steps between the reaction with an amine and catalytic acid and the reaction with an alcohol and catalytic acid. Because this isn't a good enough nucleophile or a good enough acid rather to protonate the carbonyl group, but this is a much better nucleophile than an alcohol. Or a thiol. Right? Because it's a group 5 element, which is much less electronegative. Because it's a better nucleophile than the alcohol thiol, a stronger base, it can attack the carbonyl group without waiting for the carbonyl group to get protonated. So the likely step 1 is actually the nucleophilic attack rather than the proton transfer. And after that, the mechanism's going to get kind of boring. Because the next several steps are going to be proton transfers. Right? Notice we have a neutral intermediate. And since we're in acid solution, we want to have our intermediates either be neutral or positively charged. We want to avoid any negatively charged intermediates. So what's going to be the next step of this reaction that we'll do in order to avoid negatively charged intermediates?
Protonate the oxygen.
Protonate the oxygen with what?
Is it that like acid we formed, but that wasn't strong enough to protonate the carbonyl group?
This guy? Yes.
Yeah.
So the proton shuttle in this case, the thing that takes protons off and puts protons on, is the amine, right? This is the thing that takes protons off. This is the thing that puts protons on. Now what? Keep in mind, we also, when we took that proton off, we restored it to the original amine. And you'll notice I took this and I threw it down here instead of up there. Probably a reason why I did that.
Attack the oxygen.
Take the proton
Oh,
off.
hydrogen. Never mind.
Right? Because we want to generate a neutral intermediate. So we're going to take the proton off. So step 3 is identical to the acetal formation. It was to take a proton off the thing that had just done the nucleophilic attack. But the difference is these first 2 steps are probably reversed. The nucleophilic attack happens first, and then the protonation of the carbonyl oxygen. The next 2 steps, 3 and 4, are identical. We're going to take the proton off this nitrogen, and we're going to put it on that oxygen. And in between, we're going to generate an intermediate that's neutral and looks a lot like the hemiacetal. Which is called a hemiaminal. It's A-M-I-N, not A-M-I-M. It's not an animal. So hemiaminal is analogous to the hemiacetal. 3 steps, just as it was for the hemiacetal, but with the first 2 steps reversed, and the proton shuttle being the amine instead of the alcohol. Now we have just regenerated this hydroxylammonium. We can use it to protonate the OH group, which we need to do because eventually we're going to want to use that carbonyl oxygen as a leaving group with the loss of water. So steps 3 and 4 is that proton taxi, picking up a hydrogen off the nitrogen nucleophile and adding it to the carbonyl oxygen to turn it into a good group. Now what?
I think the water's gonna leave.
The water's going to leave. And in fact, it's going to get pushed by the nitrogen lone pair. And that's an even better reaction than pushing the water out with the oxygen lone pair in the alcohol case, because the nitrogen lone pair is more basic. So water is going to leave. But still, there's not a lot of water in solution necessarily. And we're going to generate an intermediate. It looks like that. That is an iminium salt. Remember that the chloride ion has been sitting watching this the whole time. So this is basically just a protonated version of the imine that's a salt with the chloride. So that was step 5. And you'll notice that step 5 is loss of the leaving group, just as step 5 was in the case of the acetal. So it's a very similar mechanism. If you know the acetal formation mechanism, the imine formation mechanism is very similar. Different proton transfer, different order in the first 2 steps. But steps 3, 4, and 5 are identical. Step 6 is different though. Because we have another hydrogen here in the case of the primary amine, which we didn't have in the alcohol, right? Because the alcohol started with only 2 bonds to it. The R group, in this case the R group is the hydroxyl, and the 1 hydrogen. And we remove that 1 hydrogen from the acetal here in step 3, right, from the alcohol. Here we have that second hydrogen. And because we have that second hydrogen, the last step of this mechanism, instead of another nitrogen attacking, will be removal of that proton to generate a neutral imine. The product will look like this. This is an imine. The old name for imine that you'll see in some of the old literature is named after the German guy that started characterizing it. It's called a Schiff base. And this particular imine is an oxime because it has that nitrogen attached to the OH group. Oximes tend to be crystalline products. Nice sharp melting points. And so oximes, which is the derivative of reacting in a carbonyl compound with hydroxylamine, are often used, or were often used before the advent of modern spectroscopic techniques, as a way to identify carbonyl compounds. So if you had a carbonyl compound and you thought it might be acetaldehyde, you could do this reaction with hydroxylamine, form this oxime, and melt it, and see if the melting point matched what's reported in the literature for the oxime formed from acetaldehyde. And there are tables with huge numbers of melting points for oximes and other imine derivatives with different amines that are crystalline, and you can look them up, right? So you might make 2 or 3 imine compounds from a carbonyl compound and look and see which starting carbonyl compound gave matching melting points for all those different derivatives. Now we don't really need that because we've got IR, we've got NMR, we've got mass spectral analysis. But before that became prevalent, you had to do wet chemistry techniques to identify things. So 6 steps instead of 7. Different order of the first 2 steps, and step 6 is a deprotonation instead of a second nucleophilic attack. There's just 1 nucleophilic attack, right in the beginning in step 1, and 1 loss of the leaving group in step 5, like the second to last or penultimate step. Questions on this mechanism? I apologize for the fact that it starts here and ends there. I probably should have started on the far left. So let's try this again. But let's use a secondary amine instead of the primary amine and see how that might affect the reaction. You'll notice I drew every step as an equilibrium. This is a reversible reaction. If you take an imine and treat it with concentrated aqueous acid, you can get it to reconvert, to break the amine and form the carbonyl compound again. So you should try that mechanism on your own. Treat it with aqueous acid, see if you can come up with 6 steps that go through the same set of intermediates that regenerate the carbonyl compound out of the amine. So let's use a secondary amine. I'll switch aldehyde to use benzaldehyde. And the amine I'm going to use is morpholine. Which is actually an amine that you're going to use later in the lab. And you're going to react morphily with a carbonyl compound and try to figure out what the products are. So we're going to use morpholine and we're going to use catalytic molar HCl. The reaction actually will go even without the catalytic acid, but it goes better with some catalytic acid. You might use dilute sulfuric acid, like 6 mole of sulfuric acid. 12 molar HCl is pretty common. Aldehyde and amine, in this case a cyclic amine, although that doesn't really matter. It could be an acyclic secondary amine like diisopropylamine that would still work. So what happens? What's the first step of the mechanism for reacting benzaldehyde with morpholine?
Can the pair of the nitrogen attack?
So the nitrogen lone pair is going to attack the oxygen. That's the first step of the reaction with the primary amine. The secondary amine lone pair is actually even a little bit more basic than the primary amine because it has 2 alkyl groups pushing electrons towards it by hyperconjugation. So that should be a pretty favorable reaction. So step 1 is nucleophilic attack. Not different than the secondary amine and the primary amine. What's step 2?
Protonating the oxygen.
Protonating the oxygen with what?
Like the acid form of your morpholine.
That, because as soon as you add the 12 molar HCl to the morpholine, you make that, right? So you've got that going on. It's not really an equilibrium. I shouldn't show it's an equilibrium, right? Because it's a strong acid, it gets protonated. So this is going to protonate the oxygen. And convert our neutral intermediate into a positively charged intermediate. And then what? Anyone can jump in. Doesn't have to be the same person every time. What would be next? What was the product of step 3 when we reacted with the hydroxylamine?
Deprotonate the nitrogen.
Deprotonated the nitrogen, right? Take that off. To turn that positively charged intermediate into a neutral intermediate. You'll notice that as we go through this mechanism, we switch back and forth from positively charged intermediate to neutral, to positively charged to neutral. Never going negative because we're an acid. Our intermediates alternate between being charged and not being charged. So the intermediate after 3 steps is the hemiaminal, just as it was for the primary amine. But now the hemiaminal doesn't have any hydrogen attached to the nitrogen anymore, because it started with those 2 carbons. What would be the next step? The other product, obviously, is regeneration of the morpholine, the protonated form of morpholine. So you notice we start with morpholine unprotonated. You have a protonated form, then we have it unprotonated, then we have it protonated again. So as we switch back and forth from the negative or from the positively charged intermediate to the neutral intermediate from our aldehyde, we also switch back and forth from neutral morpholine to morpholinium ions.
We want to protonate the oxygen.
We want this to become water, right? Because we need it to leave as water. And it's not going to leave as a negatively charged hydroxyl group. So we're going to have to protonate it so it can leave as neutral water. So steps 3 and 4 are the same proton shuttle that we saw in all the other mechanisms, where we take the proton off the thing that was the nucleophile earlier and put it on the carbonyl oxygen and convert it into a Notice that the reason this can't work with a tertiary amine is if you were a tertiary amine, there'd be no hydrogen here, right? That would be another R group, which means there would be no hydrogen here. So step 3, that proton transfer, would not be possible. And because you can't take that proton off, because there isn't one, this reaction just reverses and you never get any further than this second intermediate in the case of the tertiary amine. So the next step is?
The water leaves.
Push the water out of there with this lone pair to generate your iminium salt. When water leaves, we often show it by just putting a little arrow there saying minus H2O. Right? So the water doesn't matter. We have the iminium salt. So now what? Actually, I did not mean to start with benzaldehyde. I meant to start with acetophenone. I'm going to sneak in here and quickly change that to the order that it was supposed to be. And you'll see why in a second. All of these steps are independent of whether the carbonyl group that you started with was an aldehyde or a ketone, because this methyl group has just been sitting there watching. So now what? The 6th step of imine formation would be to take that second proton off the nitrogen. But there's a problem. There is no second hydrogen on that nitrogen. So we can't take the proton off the nitrogen. You have to take it off the adjacent carbon. The carbon is next to that pi bond. So step 6 is still a deprotonation. But that carbon instead of nitrogen. So our product no longer have that carbon-nitrogen double bond. We'll have this carbon-carbon double bond instead. You know that these protons are next to the carbonyl group have a pKa in the range of 20 to 22. They're significantly more acidic by virtue of being next to the carbonyl group. They're even more acidic when they're next to a positively charged carbon-nitrogen double bond like this. So taking this proton off is quite favorable. You'll notice that when we do it, we also regenerate this. Right? So we regenerated our acid catalyst again, just as we have in the reaction. So now we have an enamine. This is the best resonance structure for the enamine, but there is a resonance structure for that enamine that looks like that, where this lone pair comes in and pushes the negative charge out on the carbon. That's a minor resonance contributor because it has that charge separation, but it's very important in looking at the reactivity of enamines. Enamines can be alkylated at this adjacent carbon because of the presence of the minor resonance structure. So mechanistically, enamine formation looks almost identical to imine formation, except that in step 6, because there's no hydrogen left attached to the nitrogen, we have to take it off the adjacent carbon. And with benzaldehyde, we would have been stuck, right? We would have stalled out at this enamine. There'd been no hydrogen that could be removed, and the reaction would simply have reversed. So there is no reaction between benzaldehyde and morpholine overall. It requires an alpha carbon. And in fact, it requires an alpha carbon-hydrogen bond. There's got to be what we call an enolizable hydrogen, something attached to the adjacent carbon. This carbon adjacent to the carbon. So let's take a break. It's about 9:30. Yep. Let's take a 10-minute break, and then we'll come back and we'll talk about what these enamines can do once you form them. We'll have about half an hour to talk about that. Are there questions? I'm going to leave that up for a while in case you're taking notes and you want to finish copying that stuff down. And I'm going to stop the video.
This won't work with an aldehyde, it only works with a ketone.
It will work with an aldehyde, but it has to be an aldehyde that has a carbon-hydrogen bond adjacent to it. Otherwise, there's no step 6 because there's no alpha hydrogen that can be removed.
This was an issue because we kept the aromatic ring.
Correct. You can't take you can't take the aldehyde hydrogen off because it's not in a beta position. It's attached to the carbonyl group. It has to be in the carbon adjacent to it. So it would have worked fine for acetaldehyde, right? Because there was that CH3 group on there, but for benzaldehyde it didn't work.